Hello students, now we are going to second lecture, that is AC voltage applied to a inductor. AC voltage applied to a inductor. Okay, so you know inductor representation, and we are drawing that circuit. So this is inductor, AC voltage applied to an inductor. So we know that voltage Vm sin omega t, it is going to inductor which has inductance L. So by Kirchhoff loop rule, we know that sum of voltages is equal to 0. EMF, it is represented by like this. So that's equal to 0 in one loop. So Vm sin omega t minus L di by dt is equal to 0. Okay, L di by dt is equal to 0. So L di by dt is the voltage across inductor. Voltage across inductor is L di by dt. Okay, so we know that Vm sin omega t minus L di by dt is equal to 0. So we can find that I from here. So Vm sin omega t, that's equal to L di by dt. Vm by L sin omega t, that's equal to di by dt. So we can integrate this by rearranging like this, and by integrating we get that I is equal to Vm by L sin omega t integral, that's equal to minus cos omega t divided by omega. We know that sin omega t integral, that is minus omega t divided by constant omega. So by rearranging, minus Vm by L omega cos omega t. So we get that current I is equal to minus Im cos omega t. So that cos omega t can be rearranged as cos omega t minus cos omega t is there. So minus cos omega t is changed as I is equal to Im sin omega t minus pi by 2. Sin omega t minus pi by 2 is minus cos omega t. Okay, minus cos omega t is equal to sin omega t minus pi by 2. How we get that minus cos omega t is sin omega t minus pi by 2? We know that cos theta is equal to sin of 90 minus theta. Cos theta is equal to sin of 90 minus theta. That you know that equation. Okay, so minus of cos theta, that's equal to minus of sin 90 minus theta. Minus sin theta is equal to sin of minus theta. So sin of minus 90 plus theta. So sin theta minus 90. So minus cos theta is equal to sine of theta minus 90. Here minus cos omega t, that's equal to sine of omega t minus 90. That is 90 is pi by 2. So sine of omega t minus pi by 2. So I is equal to Im sine omega t minus pi by 2. So in AC applied to an inductor, V is equal to Vm sin omega t, but there is a phase change in current. I is equal to Im sin omega t minus pi by 2, so that current lags voltage pi by 2. So and also Im is equal to Vm divided by L omega. Vm divided by L omega. Okay, Im is equal to Vm divided by L omega, and I is equal to Im sin omega t minus pi by 2. That is current lags voltage by pi by 2. Okay, so this is all about the AC applied to an inductor. So we should know, by studying an AC applied to an inductor, inductive reactance. What it is? Inductive reactance. Inductive reactance. So that inductive reactance, it is represented by XL. So we get that the peak value of current as Im is equal to Vm divided by L omega. Okay, so we know that I is equal to V by R in resistor. So here the inductor Vm divided by L omega. So we can see that XL is equal to L omega. So the inductive reactance, that's equal to XL is equal to L omega. We know that L omega, L into omega is 2 pi f. L is equal to 2 pi f. So we can write this as 2 pi f into L. So the dimension of the inductive reactance is same as resistance. So the dimension is same to resistance. SI unit is, we know that, ohm. The inductive reactance limits the current in a purely inductive circuit in the same way as the resistance limits the current in a purely resistive circuit. Okay, so the inductive reactance limits the current in a purely inductive circuit. The inductive reactance is directly proportional to inductance. Okay, so inductive reactance, we know that L omega, it is directly proportional to inductance, and also the frequency of that current, inductance and the frequency of the current. For DC, we know that DC is equal to frequency is equal to 0. So the inductance XL, that's equal to 0. So the inductor offers AC path to DC. Inductor offers AC path to DC. DC is frequency 0. So the inductive reactance is equal to 0 because inductive reactance formula is L omega. So for DC, inductor offers an AC path. The value of XL increases as the frequency is increased. So that offers a resistive path for AC. So the inductor offers resistive path for AC path to DC. So the graph we can represent it as, the graph we can represent it as, so this is representing the voltage, like this voltage is going, this is phase, omega t, but the phase is changing for current. The voltage V is equal to Vm sin omega t, and current I lags in inductor, that's equal to Im sin omega t minus pi by 2. So there is a pi by 2 change. Pi by 2 change is there. So we have to change by pi by 2. So it lags. When it starts from 0, it starts from negative, and it lags when it is maximum. It lags by pi by 2. Okay, so you understood? And also the amplitude is changes as Im is equal to, we know that Vm divided by L omega. So this is all about inductor, and also we have to find what is the phasor diagram. It is very important in the case of inductor. That is, this is y-axis, this is x-axis. We know that the voltage, it is the phase Vm sin omega t. The phase is omega t, and we have to represent current by omega t minus pi by 2. So omega t is there, and it is pi by 2 change. The current is pi by 2 lags. Okay, pi by 2 lags by current. Okay, but the current amplitude is less, so we have to reduce the length of that current. Okay, so the length is small, and it is current lags by pi by 2. Okay, and what about the power dissipated? Power dissipated in the inductor. So the power dissipated in an inductor. Okay, so the power dissipated in inductor, we know that instantaneous power P is equal to IV. So instantaneous power P is equal to, we know that I is equal to minus Im cos omega t into Vm sin omega t. So that's equal to minus Im Vm cos omega t sin omega t. So we can multiply into 2, multiply by 2 and divide by 2. Minus Im Vm by 2 cos omega t sin omega t, that's equal to sin 2 omega t. So minus Im Vm by 2 sin 2 omega t. Why we change like this? Because we get the instantaneous values here, but the average value P bar is equal to P average, that's equal to minus Im Vm by 2 sin 2 omega t. So this is a constant, minus Im Vm by 2 sin 2 omega t average, that's equal to 0. So the power dissipated in a complete cycle P is equal to 0 for an inductor. Okay, so you should remember how it is finding the average power in a complete cycle. So the average power supplied to an inductor over one complete cycle is 0. And we just remember the inductive reactance XL is equal to L omega, that's equal to 2 pi FL, and also peak value of current, that's equal to Vm divided by XL. Okay, and next we have to study the capacitor. So the AC voltage applied to a capacitor, how it is going. AC voltage applied to capacitor. So we know that the diagram, it is AC going through a capacitor. We know that the symbol of capacitor, two parallel lines C, is representation of capacitance. By applying Kirchhoff law, we know that Vm sin omega t minus Q by C is equal to 0. Why Q by C? V is equal to Q by C. We know that voltage across a capacitor Q by C. So we find that current by Q by C is equal to Vm sin omega t, and Q is equal to C Vm sin omega t. So we know that the charge is here. So we have to find d by dt of charge, that's equal to current, that's equal to C Vm is a constant, and d by dt of sin omega t, that's equal to, we know that I is equal to C Vm d by dt of sin omega t is equal to cos omega t into omega derivative, that is multiplied by the constant omega. So C omega Vm cos omega t. Okay, so C omega Vm, that's equal to Im. So I is equal to Im cos omega t. The cos omega t can be represented as cos omega t as represented as sin omega t plus pi by 2. Okay, cos omega t can be represented as sin omega t plus pi by 2. Okay, so I is equal to Im sin omega t plus pi by 2. So we can get that voltage V is equal to Vm sin omega t, and I is equal to Im sin omega t plus pi by 2. That is, current leads the voltage by pi by 2. Okay, so how we write that cos omega t is equal to sin of omega t plus pi by 2? We know that cos theta is equal to sin of 90 plus theta. So we can write as cos omega t is equal to sin omega t plus pi by 2. That is, theta and 90 can be interchanged, no? So that is the thing we are doing here. And the current amplitude Im is equal to C omega into Vm. We know that Vm divided by R, Vm divided by XL. So something divided by the reactance. So the capacity reactance, that's equal to 1 by C omega. So Im is equal to Vm divided by XC. XC is the capacity reactance, that is equal to 1 by C omega. So Im is equal to C omega Vm. So the capacity reactance, you have to remember that formula. Im is equal to Vm into C omega. That means Vm divided by 1 by C omega. This 1 by C omega is capacity reactance XC. So this is the capacity reactance. It is the resistance offered by capacitor. So the resistance in resistor to analogous like in capacitor, that is capacity reactance. The SI unit of capacity reactance is also ohm. The capacity reactance limits the amplitude of current in the purely capacity circuit in the same way as the resistance limits the current in a purely resistive circuit. Capacity reactance is inversely proportional to frequency. So we know that XC is equal to 1 by C omega. So that's equal to 1 by C into 2 pi F. That is capacity reactance inversely proportional to frequency. So for DC, frequency is equal to 0. So the capacity reactance is equal to infinite. So the capacitor blocks DC. Capacitor blocks DC. But for AC, XC is inversely proportional to frequency. For AC, the frequency increases the capacitive reactance decreases. So capacitor LO AC. Capacitor LOAC. So this is opposite to that of inductor. So you should remember inductive reactance as L omega, XC capacitive reactance as 1 by C omega. And what about the graph and phasor diagram in capacitive capacitor? So we know that current leads in this. So when we are drawing that voltage graph, we know that like this, it is phase is omega t, but when it is omega t, it starts from 0, the current leads by pi by 2, but the amplitude is less, but it is, when it is 0, it is maximum, it is 0, it is 0, it is maximum, like that it is going. Okay, so current leads by pi by 2, omega t plus pi by 2. Okay, the phasor diagram, it is represented by, we know that the voltage, it is represented by a vector V, and the phase is equal to omega t, and the current phasor, it is less, length is small than voltage, but it is increased by pi by 2, that is the angle is pi by 2 more than that of voltage. Okay, that is current leads in capacitor. AC applied to a capacitor, current leads. In an inductor, current lags. And what is the power? Power that's equal to P is equal to IV. The instantaneous current that's equal to Im cos omega t, Vm sin omega t. So that's equal to Im Vm divided by 2. We know how to multiply by 2 and divide by 2. So that's equal to Im Vm by 2 sin 2 omega t. This is instantaneous, and the average, that's equal to Im Vm divided by 2, average of sin 2 omega t, that's equal to 0. So the average power dissipated in a capacitor over one complete cycle is equal to 0. For inductor and capacitor, average dissipated power over a complete cycle is equal to 0. And you should remember the capacitor reactance is equal to 1 by C omega. So the DC is equal to omega, frequency is equal to 0. So a capacitor blocks DC, capacitor LO AC. Okay. So this is all about AC applied to a capacitor and AC applied to a capacitor and inductor circuit. So thank you guys.